Hi everyone. From our previous lecture, we know the energy spectrum of beta particle, that is beta particle emitted, yield of beta particle with energy must be a discrete graph. That is, the energy of beta particle emitted in a particular beta decay should give a constant energy of a beta particle. That was our theoretical prediction. But experiment shows the energy of emitted beta particle, it is not discrete. It's vary from a maximum to minimum, and this is the experimental result. Experimental results suggest that the energy of emitted beta particles should vary this kind. That is, the number of particle yield and energy of that particle will vary by this kind of graph. And this graph is shows the energy is discrete, and this variation is due to the resolution of the observing device or detector. As different kinds of detector detects the energy of particle different, so this shows the variation of those energy measured. That was our theoretical prediction, and experimental shows that the graph look like this. To verify this experimental results, the first calculation was given by Fermi and is called the energy calculation for beta spectrum. In beta decay, the spectrum I shown you, the beta spectrum's energy can be calculated by this way. We have to consider a parent nuclei which is breaking into daughter nuclei, and we know in beta decay, when a parent nuclei breaks into daughter nuclei, it gives a beta particle and neutrino or anti-neutrino. Here I am considering it gives neutrino. So at initial parent case, we have the wave function psi p, and in final case, we have to consider the wave function for daughter nuclei psi d, wave function for neutrino, and wave function for beta particle. Now, the number of particle emitted in a beta decay will be proportional to the transition probability. Transition probability symbolized by this symbol lambda, and it's equals to 2 pi divided by h cross h suffix if mod square dn divided by def. Here the dn divided by def is the energy density of the final state. Now we have to calculate the HIF value and the dN divided by DEF value. That is the energy density or state density in per unit energy. Let's first calculate the HIF. Calculation for HIF. HIF is given by integration over the entire volume of the nucleus d tau of the initial wave functions complex conjugate psi I star perturbated Hamiltonian with the final wave function psi f. So it will give integration of psi I equals to psi p, perturbated Hamiltonian will remain as it is, and psi f is equals to psi daughter, psi beta, and psi neutrino integrated over the entire volume d tau. Now we have to consider the wave functions for beta and neutrino. From our general expression, we know the wave function for any particle. Let's first calculate wave function for neutrino psi nu. That will be equals to 1 divided by root v times exponential iota p nu, that is momentum of nu dot product with the radius r vector divided by h cross. And if you calculate the energy or momentum of beta particle p nu, we have to take the formula E nu square equals to P nu square C square plus M nu C to the power 4. M square C to the power 4. Now, initially we are taking the mass of neutrino as 0. That is our assumption. We don't know much information about neutrino. So when Fermi calculated at first this in this way, he considered the rest mass or mass of neutrino is equals to 0. So this term whole equals to 0. And we get for E nu equals to 1, that is if the energy of neutrino is 1 MeV, in that case we get P nu equals to 1 divided by C. So this term P nu r dot P nu dot r divided by h cross will become, and we are taking radius equals to 1 Fermi. So we will get P nu dot 1 Fermi divided by h cross. This term I am calculating here. So it will equals to P nu, we get 1 divided by C. So C times h cross. And this, if you calculate, this will give the result nearly equal to 10 to the power negative 2. So this whole term equals to 10 to the power negative 2. Now if you expand this exponential term in binomial expansion or any kind of expansion, you know this is the exponential. So it will give 1 divided by root v times 1 plus 10 to the power negative 2 plus dot dot dot, neglecting higher order terms, and this 10 to the power negative 2 is much smaller in compared to 1. So we are assuming this term as 0. So our final result is psi nu equals to 1 divided by root v. We are putting, so we have to put this psi nu equals to 1 divided by root v. Now let's take the wave function for beta. Similarly, psi beta will be 1 divided by root v iota momentum of beta dot r vector divided by h cross, same as our previous case. So if you calculate the beta particles momentum, we have to take the energy of beta particle times momentum of beta particle and rest mass square of beta particle m beta square into c to the power 4. Now this term in this case is not equal to 0, and if you calculate the momentum for beta particle, you will get 0.86. Similarly, if you calculate the P beta dot r vector divided by h cross, taking r equals to 1 Fermi, you will get it's nearly equals to 10 to the power negative 3. In our previous case, we get 10 to the power 2, negative 2. Here it is equals to 10 to the power negative, 10 to the power negative 3. Again, by expanding this exponential term, you will get the psi beta equals to 1 divided by root v times 1, neglecting 10 to the power negative 3 term. So we will get psi beta equals to 1 divided by root v, psi nu equals to 1 divided by root v. So our hf will be equals to 1 divided by root v are constant. Taking outside of integration, we will get 1 divided by root v times root v, that is v integration over psi p Hamiltonian, perturbated Hamiltonian, and psi daughter times d tau. Now if you know the wave function for parent nuclei and daughter nuclei, you can calculate this whole integration term. And we are symbolizing this whole integration term as MIV. So our HIV will be equals to HIF will be equals to MIF divided by V. This whole integration term is denoted as MIF. So HIF equals to MIF divided by V. So our transition probability, which will gives us the beta particle emitted, number of beta particle emitted, is equals to this HIF equals to MIF divided by V and its mod square. Now we have to calculate dN by dEF for this transition. For that we have to consider the energy of each of particle. Energy of each particle, that is, we have to take energy of neutrino, energy of beta particle, that is, now calculating this dN divided by dF. For that, the energy of the system will be equals to E nu plus E beta. Now this E nu equals to P nu times C, and this beta particles energy is equals to MEC square plus kinetic energy of beta, not E, it's beta, m beta c square plus kinetic energy of beta, as energy can be calculated as rest mass energy plus kinetic energy. And for neutrino, E nu square equals to m nu square c to the power 4 plus p nu square c square, as this term for neutrino is 0, rest mass of neutrino is 0, we are taking that, we are considering the mass of neutrino as 0, so we get energy of neutrino is equals to P nu C. So this is given here. So our D, so EF equals to this, final state's energy is this, and we have to take the differentiation of this energy, that is DEF will be equals to this mass, and c square is a constant term, and if you consider for a reaction the energy of beta particle is a constant, then you will get DEF equals to dP nu times C plus this terms will be equals to 0. So DEF equals to dP nu times C. Now we have to calculate the small dN value. What is small dN? dN is nothing but total volume V total divided by small volume dV. So V total is equals to integration over dx, dy, dz, dpx, dpy, dpz divided by small dv equals to h cube. If you consider phase space, in that case you will get this axis is x and this one is z, this is y. If you consider a circle in phase space, the small volume dv will be equals to h cube, because this is the minimum volume that can be occupied by a particle in phase space. So dv equals to h cube, and this dv is equals to this dx dp dz dpx dp dpz, and this df dpx dpy dpz equals to 4 pi p square dp. So we are replacing this dx dy dpz as v when integrated over volume. This one is v, and dx integration of dpx dpy dpz as equals to 4 pi p square dp. So v times 4 pi p square dp. This will be the dn value. So this is our dn value. So this is the general expression for dn. And now if you consider the final state's dn value, in that case dn will be equals to, so in final state dn total is equals to dn for neutrino times dn for beta. We have to multiply this term with p nu dp nu times again for v times 4 pi p beta square dp beta divided by h cube. So we get v into 4 pi divided by h cube. This, so we get the dn value equals to 4 pi v divided by h cube square times p nu square p beta square dp nu dp beta. So we get this def value and dn total value, but to calculate dn we still have to evaluate the values of p nu, p beta, dp nu and dp beta. So let's see what are those values. To calculate p nu, we know the q value is shared between the kinetic energy of beta particle and energy of the neutrino, that is p nu c. This equation we have seen previous. From this equation we can say the p nu value, p nu equals to q minus k beta divided by c. We got p nu, we have to find the p beta value. So for p beta we have to take the equation energy of beta particle is equals to rest mass of beta times c square plus plus kinetic energy of beta particle. Rest mass energy plus kinetic energy. So k beta is the kinetic energy of beta particle, and this E beta can be written as m beta square c to the power 4 plus p beta square c square power half. So this equals to m beta c square plus k beta. Now if you want to remove the under root sign from this equation, we have to take square on both hand side. So taking square on both hand side, we get this whole term square. Now breaking this term as a plus b whole square, you will get this equals to m beta square c to the power 4 plus k beta square plus twice of m beta c square times k beta, and this hand side is as it is. So this is m beta square c to the power 4 plus p beta square c square. From both hand side, the m beta square c to the power 4 and m beta square c to the power 4 get cancelled, and from this equation we can easily get the value of p beta, that is nothing but 1 by c times k beta square plus twice m beta c square k beta whole power half, that is in under root. And by differentiating it by with k beta, you will get dp beta, because you have to find the value of p beta and also dp beta. So from this equation, dp beta will be equals to 1 divided by c and divided by 2. This power will be get multiplied, so this became 2, and under root this whole term, that is k beta square plus twice m beta c square k beta, and at the upper side we have differentiating it, you will get twice k beta plus, from this you will get twice m beta and c square times d k beta. So these are the values of p beta and dp beta. So p beta, so by taking those values we can write the dn and def, that is the lambda value can be written as lambda was 2 pi divided by h cross mod of HIF, and we have calculated that HIF value is nothing but MIF divided by V square, and we have the value of dN and dE, so let's put those values, that is 4 pi, here it was dN divided by dEF. So this is the dN value, so let's put dN by dEF value. So dN is 4 pi V divided by H cube whole square times P nu is Q minus K beta divided by C whole square, P nu square, and we have P beta square, so this is P beta square, so let's put P beta square, 1 divided by C times K beta square plus twice M beta C square K beta power half, and the d beta, this was dp beta value, so this get multiplied automatically, and finally we have the dp nu here, so this was multiplied by dp nu, and at the bottom we have this value dp nu by c, so dp nu times c. So this dp nu and this dp nu get cancelled, and we have finally this equation for transition probability value lambda, and we know in beta decay the number of beta particle emitted is proportional to this transition probability lambda. So in next stage what we will do, we will equate this transition probability to the number of particles emitted in energy k beta to the range dk beta, that is n k beta dk beta is proportional to this lambda value. By proportionaling this nk beta, you will get the value of nk beta, the all constant term will be get vanished. So finally we will have the value for nk beta dk beta proportional to this term, and this dk beta can be cancelled out. So we have the value for number of particle, beta particle emitted is proportional to this whole term. Sorry, I have done a mistake. That is, this is our value for p beta, but we have to multiply this with p beta square. So this power half will be get squared, but as at below we have the same term in under root, so this will get under root and this term will get vanished, and this 2 will be also get vanished. So finally we have this value, that 1 by c times this and this power half. So this is this number of particle yield is proportional to this term. C is a constant, so it can be removed by taking the proportional sign. And from this equation, if you know the value of Q and kinetic energy of beta particle, and if you plot the kinetic energy beta particle versus the number of beta particle yield, you will get this kind of graph. That is, if this axis is number of beta particle with kinetic energy k beta, and this is the energy of those beta particle emitted, that is k beta, you will get this kind of graph. From this equation you will get this kind of graph. But in actual cases, if you do the experiment and in precise measurement, this graph really get diminished at this point. So this is difference causes by the assumption neutrino as massless particle. As we have assumed neutrino has no mass, from this assumption we have done a mistake, and from this mistake, if you put those mistake here, you can easily calculate the mass of neutrino. And the correction factor for beta plus and beta minus decay can also be calculated, and we don't have to calculate those correction factor. I am writing this correction factor if d is nothing but 2 pi eta divided by 1 minus e to the power minus 2 pi eta, where this eta value, eta equals to zd square divided by 4 pi epsilon naught v times h cross. This v is the energy velocity of the emitted beta particle, and this is plus minus. Minus for beta plus decay and plus for beta minus decay. And if you put this correction factor, means if you put this fd, that is n effective, will be proportional to fd times nke, k beta or ke. If you do this, you will get the graph for beta plus decay also. So this is the graph for beta plus and this is for beta minus. So that's all in Fermi's calculation of beta particle emitted in a nuclear reaction or nuclear decay. If you like this video, please feel free to give any comment in the comment section, and please subscribe this channel if you want this kind of video in future. Thank you.